make sure you do those papers that I've already sent, and we'll discuss those later. So this one is that you're given a question and you're being told that which part is this? This one. So you're given a question and you're being told that chlorine gas is reacted with aqueous NaOH. The oxidation number of chlorine changes from 0 to -1 and also from 0 to +1. So which one is this? Now this is something that you have to remember. If I open the inorganic notes, okay, have I sent these notes to you?
No, sir, I don't think you have.
So
No, sir.
I'll try and send these. So inorganic is basically just memorization. So this is about group 7. So when you look at group 17, this one, you would notice there's this reaction over here that you have to remember, which is a disproportionation reaction. This one, it is a reaction in which chlorine undergoes both oxidation and reduction at the same time. So if you reacted with cold NaOH, it forms NaCl, NaClO, and H2O. If chlorine is reacted with hot NaOH, it forms NaCl, NaClO3, and water. So two different things are produced, sodium chlorate 1 or sodium chlorate 5. You have to remember these equations. Now, if I go back to the question, he's saying that chlorine changes from 0 to +1. So it's probably the cold one. Like this was the equation that if you react NaOH, just a second. So if you react NaOH with Cl2 in cold, it will form NaCl and it will form NaClO and it will form H2O. Those are going to be your products. But that's with cold NaOH. And the oxidation state of Cl over here is -1. Over here, Cl is +1. Like if you try and calculate this, this is going to come out to be +1. Na is +1, O is -2, so Cl would be +1. But anyways, under which conditions does the reaction occur? And what is the color of the solid silver salt which chlorine? So first thing, the conditions. They got to be cold. It's got to be cold, dilute, NaOH or alkali. And then you have the precipitate of chlorine, like the silver salt. This is the next thing that you also have to remember in, it's the test for halide ions. Like when you have silver Cl-1 and you add silver ions, these were tests that you did in O levels as well. So these are tests. Cl-1 with silver ions produces a white precipitate of AgCl, which dissolves in NH3. Br-1 on the other hand produces a green precipitate with silver ions, and I-1 with silver ions would produce a yellow precipitate, which is not going to be soluble in NH3. So in this case, it's going to be a white one because Cl-1 is involved. So the answer to this one would be the color of the silver salt is going to be, it's going to be white in color. So just make sure I'll send you these notes. Most of the stuff related to these notes, that's got to be remembered. That's just got to be memorized. Disproportionation, the test of the ions, that's got to be remembered.
Sir?
Yeah.
The notes you're gonna send, it's in a PDF version, and is it one page? Because I tried to print out the notes you sent, but I couldn't because it was only one page.
Which one?
These ones are. Is this one page or like is it many?
No, this is like 5 pages. So you've got period.
Oh, okay, it's split up, right? Because the board notes which you send, right? I can't split them up. That's right.
I said, they're actually. So I get your point. The board notes are always like one page, like one.
Yeah. Is there a way to split them up?
I'm not sure, but there must be a way to print it out. I mean, it's like, doesn't it split it up automatically?
No, for me it didn't, for some reason.
But did it get printed out?
No, I didn't print it because it was only one page. It was showing the preview as one page, and then I had an A4 paper, so it would come up as really small.
No, just.
But I'll try.
Make sure you like I think it should, like the remaining pages should print on the other pages. I mean, there must be a way to do that. I'll check that
No,
after
I'll
this
see.
class.
I'll search for something. Okay. Okay. Thank you.
Sir, could you explain how you knew which one's +1 and -1?
These two,
Yes.
that's you calculate the oxidation state. Like any, group one is always +1, right? Oxygen is always -2. Cl is the
Yes.
unknown. So that is taken as X. So all of the charges must add up to be equal to 0 because it's a neutral molecule.
Yeah. Okay.
So when you solve this, it comes out to be +1. And
Yeah.
this one is the same way. Na is +1, group 1. So Cl has to be -1. So
Yeah. Okay.
next,
Thank you, sir.
the next question, again, it's about when concentrated sulfuric acid reacts with sodium iodide, the product includes sulfur, iodine, and hydrogen sulfide and sulfur dioxide. Which statement is correct? Now, this particular reaction, I'll go through the notes again, and this is about group 17 again. So if I go through the notes, group 17, remember one thing about this thing. Halides can act as good reducing agents. The bottom one are stronger reducing agents. The bottom two, actually, they're really good reducing agents because if you have I-1, it can lose electrons to form I2. The reason it can lose electrons very easily is that it's a big atom. Big atoms, the electrons are really far away from the nucleus. So it doesn't have a very strong tendency to attract electrons. So it loses electrons very easily. Bigger ions are more shielded, so they lose electrons relatively easily. So I-1 really likes to lose electrons. I-1 really likes to form I2. F-1, on the other hand, doesn't like to lose electrons. It's a small atom. F is one of the most electronegative atoms. So fluorine wants to gain electrons. It doesn't want to lose electrons. So the top ones, they don't like to lose electrons. The bottom ones, they do like to lose electrons. Is the idea clear, this thing?
Yes.
Yes, sir.
So the bottom two are really good reducing agents. They get oxidized, they lose electrons. Anything that gets oxidized is a good reducing agent. So the next part was that you have to learn this thing. It's a reaction of halide ions with concentrated sulfuric acid. What happens in that case is, and let me explain that. Let me explain it on the board. Where's the board? Just a second. So I'm going to explain this over here. So first thing is, where's this one? So the first thing is F-1, Cl-1, Br-1, and I've got I-1. So the bottom one, that loses electrons easily. So that loses electrons easily. The top one doesn't like to lose electrons. When you react NaCl with H2SO4, concentrated H2SO4, there is no displacement, there's no redox reaction. Now, in this case, there is no redox reaction. Why is there not a redox reaction? Because Cl-1 does not like to lose electrons. You've got a Cl-1. Cl-1 holds on to its electrons. It doesn't like to lose electrons. It doesn't like to get oxidized. Right? Is the idea clear?
Yes.
Yes, sir.
Because in a redox reaction, somebody has to lose electrons and somebody has to gain electrons. Cl-1 is refusing to do that. It doesn't like to lose electrons. So what you instead get is a displacement reaction. Like when you mix them together, what happens is, let's say you put them in a beaker. Now, NaCl is not really going to react with sulfuric acid directly, not in a direct way. Why? Because there is no reaction. An acid reacts with a base, not with a salt. But H2SO4 is concentrated, so there's a lot of H+1 ions, there's a lot of SO4 -2 ions in the solution. Remember, an ionic compound, an acid or a base or a salt, it dissociates when it dissolves in water. Its ions, they split up. The same happens to NaCl as well. Like when you mix NaCl, the sodium ions and the Cl ions, they all mix up. That's what happens. That's what happens to the white crystal. When you mix it in water, the ions, they completely scatter throughout the solution. So is that clear?
Yes.
Yes, sir.
The next thing that happens is that when you mix them up and it's very concentrated, the H+1 and the Cl ions might get together. They might join up. I mean, the H+1 is coming from the acid, and the Cl ions are coming from the salt, and they would form HCl. Now, HCl is a gas. HCl dissolved in water is acidic, but HCl dissolved in water is hydrochloric acid. It dissolves in water if it's dilute, because the H+1 and Cl ions will be very far away from each other if it's dilute. But if it's concentrated, the H+1 and Cl ions would be really close to each other, and they would join up to form HCl gas. And that gives white fumes. You see, like if you see steam has white fumes. So there's going to be white fumes formed on top of the solution. And the H+1 and Cl ions in the solution would go away. And that would result in the formation of, so HCl gas is formed, and NaHSO4 is formed in this solution. That is, sorry, this one. So that is what is left in the solution. Is that clear?
Yes, sir.
Yes.
Yes.
I said, but then what happens if you go down the group? Pretty much the same thing happens, except that they really like to lose electrons. So if I repeat the equation with NaBr and with NaI, so I'll just replace. So you'll get kind of the same products. Sorry. One second. So you're going to kind of get the same products, except instead of the Cl you'll have iodine or Br. So I'll just replace that. So no Cl, and in their place you've got a Br. Or यहाँ पे there's a Br, and there's a bromine over here as well. Not bromine, the next one should be iodine. HI. But the thing is that they really like to lose electrons. They're big ions and they really want to. So Br-1 and I-1 really want to lose electrons. Is that clear?
Yes.
So that would result in a redox reaction. And the redox reactions are given in the notes. So this is what happens. That initially there is, for NaBr and H2SO4, you get HBr, but immediately, immediately this HBr over here, the Br-1 likes to lose electrons. So it will start turning into Br2. And who would be gaining electrons? The sulfuric acid would be the one that would be gaining electrons. It would get reduced. Sulfur is +6 over here, sulfur is +4 over here. So it will form sulfur dioxide. I-1 is an even bigger ion. It really likes to lose electrons. So that's an even good reducing agent. What happens in that case is I-1 loses electrons to form I2, and the sulfuric acid gets reduced to either sulfur dioxide or sulfur or H2S. So multiple products would be formed. Is that clear?
Yeah. Yeah.
So you remember this for group 17, remember this. This is very important. Cl-1, not a good reducing agent, doesn't like to lose electrons. So which is why you only get displacement. No redox happens, you get HCl gas, that's it. Down the group, you're still getting displacement, but now it's mostly redox. I-1 is going to be mostly redox. It would mostly be losing electrons, and the other one would mostly be gaining electrons to form all of these products. So that's the summary of this whole. So coming back to the question, what does the question state? The question is stating the exact thing, that if you react sodium iodide with sulfuric acid, you're basically getting a redox reaction. You're getting sulfur, you're getting iodine. I mean, the I-1 over here. So the I-1 over here is turning into iodine. And so which statement is correct? hydrogen sulfide is the product of a reduction reaction. This one is wrong because iodide ions were good reducing agents, not good oxidizing agents. Sulfur atoms are getting reduced. That's also wrong. They're not. It's the only thing is the first one is correct. The first one is correct, and the reason why the first one is correct is that I-1 is acting as the reducing agent, and the sulfuric acid is getting reduced in all of these options. It goes from +6 to +4, +6 to 0, sulfur is 0, or +6 to -2, sulfur in H2S is -2. So I-1 is the reducing agent, and it reduces the sulfuric acid into all these products. Is that clear?
Yes.
Yes, sir. Yeah.
So hydrogen sulfide is the product of a reduction reaction. Sulfur is a product of a reduction reaction. So oxidize this part would be wrong. And iodide is acting as the strong reducing agent, so not an oxidizing agent. So all the other ones are incorrect. Then you have this one. He's saying that there's an exhaust gases of internal combustion engines when catalytic converters. So let me just quickly go through. This is also kind of O levels. Catalytic converters must be written somewhere. Just a second, probably at the end. So catalytic converters are these things. What they do is they're right at the bottom. They're a honeycomb structure made of palladium or platinum catalyst. They're present in the car exhaust because the car exhaust has lots of unburnt hydrocarbons like fuel. It's got the air burns up, nitrogen, oxygen in the air, they heat up and they burn up and they produce oxides of nitrogen, which are poisonous. And also they cause acid rain. And then you've got carbon monoxide, which is also poisonous, which is very poisonous. So the equation over here is sort of hidden, but I'll tell you what the equation is. This is what happens. Car exhaust has all these gases, carbon monoxide, oxides of nitrogen, and it's got unburned hydrocarbons. So when they pass through the honeycomb structure, which catalyzes this reaction, the carbon monoxide turns back into carbon dioxide, the nitrogen oxides they turn back into N2. And the unburned hydrocarbon, it turns into carbon dioxide and water. So some of the substances are oxidized. The carbon monoxide is oxidized. This one is reduced. That's the whole equation. This one is reduced. And this one over here is oxidized. So these are the products. So the question is now, the first two are getting reduced and the other two are getting oxidized. So it's going to be C. The correct option would be C. Is that clear?
Yes, sir. Yeah.
So plus again, make sure you memorize the notes, like what happens when you have a catalytic converter. The next thing is this methylamine has similar chemical properties to ammonia. Mikhail, is that clear? The previous one.
Yes, yes.
Okay. So you've got the next one is methylamine. It has similar chemical properties to ammonia. It reacts with hydrogen chloride, so there's a reaction given. So what he's saying, a sample of methyl ammonium chloride is heated with aqueous NaOH. What are the products? So this reaction, when he says, the moment he says that methylamine has similar chemical properties to ammonia. So what that means is he's basically talking about ammonia. So this is more about equations that you've already studied in O levels as well. So I'll just revise one of ammonia equations, the ones that involve ammonia. There are two main equations that you have to know. Ammonia, when it reacts with acids, any acid, it ends up forming ammonium salt. What is an ammonium salt? An ammonium salt is get rid of the H in the acid, replace it with NH4 plus 1. So that's your ammonium salt. And you can You can make it with sulfuric acid, get rid of the H, replace it with NH4 plus 1. I mean, that's how salts are always produced. You just remove the H of the acid and do crisscross. So this would be NH4 twice. So that's an ammonium salt. Now the thing is that this is an acid-base reaction. Why is it an acid-base reaction? Because N over here, NH3, is acting as a base. It has a lone pair. What it does is that the acid provides it with H plus 1 ions. So over there it goes and the NH3 turns into ammonium ions. Why? Because the acid gave its H plus 1 ions, and those H plus 1 ions, they ended up forming a dative bond with NH3. So there's dative bond formation that's happening, and they would ask a lot of questions about this. This one is behaving as a base because it is accepting H plus 1 ions. NH3 turns into NH4 plus 1. It did the same thing over there as well. NH3 turned into NH4 plus 1. And where did the H plus 1 came from? It came from the acid. Is that clear, this one?
Yes, sir.
So that hydrogen, it comes from the H2SO4, right?
Yeah. I mean, it's not a
Yeah,
balanced
okay.
equation, but the acid is providing the H plus 1 ions and it's giving it to ammonia. So it's an acid-base reaction, right? Now there's another
But when it's also acid,
Which one?
you can go first.
Which one?
The above one is also acid based, right?
They're both
The
exactly
NH3.
I mean, they're both exactly the same, no matter what the acid is, whether it's HNO3, HCl, H2SO4, whatever the acid is. Even if it's an organic acid, like even if it's a carboxylic acid, you're going to get the same thing. Like if you have ammonia reacting with, let's say, ethanoic acid. So ethanoic acid is CH3COH. So this H would be given to ammonia, and ammonia would turn into, I mean, this would become CH3CO minus 1. It would lose the H, and the ammonia would pick up that H and attach it to itself. So it would become ammonium ethanoate. That's the salt. Is that clear?
Yes, sir. Yeah.
So it's an acid-base reaction. This is exactly the same. This reaction is exactly the same. He just added a carbon chain. There's a lone pair on N. The acid would give its H to that lone pair, and it would become a CH3. There's going to be an extra H added. It would become CH3 NH3 plus 1. And what's left is Cl minus 1. Is that clear? So it's the same exact reaction.
Yes, sir.
So now the other one, there's another reaction that happens now. Once an ammonium salt has been formed, let's say once you have an ammonium salt, like once you have NH4 plus 1, it's now capable of doing the reverse. Right now, this is behaving as a base over here. But once it gains an H plus 1, it can now act as an acid, because it can lose that H plus 1. It can provide, or it could be a proton donor, or it could be producing H plus 1 ions. Is the idea clear? That NH3, once it gains an H plus 1, it turns into an acid, because now it's capable of losing an H plus 1 ion. Is that clear?
Yes.
Yes.
So all these salts, whether it's this salt or any ammonium salt, they're basically acidic. They're basically acidic because now this NH4 plus 1 is capable of losing an H plus 1 because it has already gained it. So he's reacting it with NOH. NOH is a base. So what happens is that the NH4, the H plus 1 is given back to these OH ions. I mean, OH ions are basic because they accept H plus 1 ions. So if the OH ions get the H plus 1, they would form water. The NH4 will turn back into NH3, right? Because the NH4 plus 1, the H plus 1 is given back to OH ions, and that turns into water. And what's left is Na and Cl ions. So the salt that would be produced is NaCl. Now this is a standard reaction. that whenever you have an ammonium salt, it reacts with a base, it produces salt, water, and NH3. This was one reaction that you studied in fertilizers as well in O levels, that farmers should not add lime and fertilizers together because ammonia gas is produced. And this is a standard reaction that you should know, that any ammonium salt, whether it's ammonium sulfate, something similar would happen. Like if I reacted with any base like calcium hydroxide, the OH ions over here will accept the H+1 from ammonia and they will turn into water. The NH4 plus 1 has lost the H, so it's going to turn into NH3. And what's left is your salt, which is going to be calcium and SO4. So is that clear?
Yeah.
Yes.
Achha, anyway, so he's asking you to make the same type of reaction with NaOH for this one, which is this one. It's CH3NH2 plus 1. The reason I'm discussing this in detail is because there's a small topic on acid bases. So you should know that this is behaving as an acid. It's anything that loses H+1 is behaving as an acid. Achha, anyway, so we have to make a reaction with this thing, CH3, NH3 plus 1 and Cl is minus 1. So if I reacted with NaOH, so the H+1 that it had gained would go and join with the OH and it would form water. And the CH3NH3 would turn back into CH3NH2. And the other thing that would be produced is going to be NaCl. So those are going to be your three products that are going to be produced. Is that clear? So methylamine,
Yes.
water, and NaCl. So it's going to be D. And specifically this reaction, ammonia reactions. I mean, you should know all the other reactions as well, like a metal plus acid produces salt plus H2. Base plus acid produces salt plus water. But specifically this ammonia reaction, this is kind of very important, both reactions, because they link it up with acids and bases and dative bonding as well. They're going to ask you, why does it accept H+1? Because it's capable of forming a dative bond. It's got lone pairs, and the H+1 gets attracted to those lone pairs. Why is this reacting with a base? Because it's capable of losing an H+1 ion. So you should know all of this. Now, just a second. One second. Let me just. So we are on this one. Let's move to the rest would probably be organic. So we'll probably try and do. So this one is the first question is about. It's actually about isomers. So yes. So let's try a couple of them. This one is saying how many chiral centers does each acid? We did do chirality, right?
Yes.
Yeah.
So chirality was that. So chirality was that the carbon atom must be bonded to 4 different groups. It's got mirror images. So it's got 4 different groups, and they would be mirrored. There's going to be a mirrored version of this. So if this is W, this should be X, this would be Y, and this should be Z. So that is what chirality is. So is the first molecule chiral or not? The first one. Is there a carbon atom that's bonded to 4 different groups?
No, sir. The first one is not kind.
It's not chiral because if you look at this carbon atom, then it's bonded to 2 hydrogen atoms, right? So obviously that's the same type of group. If you look at the bottom one, then the carbon is again bonded to 2 hydrogens, so that's not possible. If you look at the carboxylic acid, that's out of the question because carboxylic acid is C double bond O NOH. That's what COH stands for. Anything that's making a double bond is obviously rejected because you need 4 single bonds. So the carboxylic acid ones are gone anyways, so that's out of the question. So the only one that you're left with is the middle one. Is that chiral or not? This one.
No.
No.
It's not, because the top and the bottom are the same. Like it's the other two groups are different, but the carbon is not bonded to four different groups. The top one and the bottom one are exactly the same. What about this other one? Is this chiral?
Yes, it has two chiral.
It's got two chiral atoms. So this one is chiral. Why is this chiral? Because this carbon has an H, like it's bonded to an H. OH in branches, that means OH in brackets means it's a branch. So all four groups are different. I mean, CH and OH, plus this side is different, top side. This one is also chiral, this carbon atom over here. CH means it's bonded to an H. On one side, there's a COH. At the bottom, there's a different thing, I think. Yes, there is difference, and the top is different. So this carbon atom, everything looks different as well. COH, H on this side, bottom side is this entire thing, and the top side is this one. So there are actually two chiral carbon atoms. The top one is not chiral because it's got two hydrogens. So it's going to be 0 and it's going to be 0 and 2. And that would give you D as the answer. Is that clear?
Yes.
Yes, sir.
Actually, now the next one. We haven't done this in class, but I'll just explain this very quickly. He's asking C6H14 and O. How many tertiary alcohols are possible? So I'll just quickly explain what a tertiary alcohol is. A tertiary alcohol is something that has, I'll just quickly explain this. It's a simple concept. There are three types of alcohols. The first one is a primary alcohol. A primary alcohol is that if you have a OH bonded to a carbon atom, then on one side there's a carbon chain, but on two sides there are hydrogen atoms. That's a primary alcohol. A tertiary one would be, a secondary one would be that you've got an OH bonded to a carbon atom, and on two sides there are carbon chains to that carbon atom. And a tertiary one, all three behave differently, which is why differentiating them is important. That's a tertiary alcohol. That the carbon on which the OH is bonded, it's bonded on three sides by a carbon chain. So you've got C6H14O. And we're going to try and figure out how many C6H14O can we have. And so it's kind of like related to isomerism. So C6, H14, and O. So the first one would be 6 carbon atoms in a straight line, right? So that is, you've got an OH here. What other combinations can I have? C6, H14, and O. So I can have positional isomers. What I can do is I can have the OH on the second one. Or what else? Now I would have to make a lot of them. So I can have 6 carbon atoms and the OH is on the third one. So on a straight chain, those are the only 3 possible positional isomers. Is that clear?
Yes, sir.
Yes, sir.
Yes.
Asha, then I'll make a chain isomer. Like what I'll do is I'll have 5 carbon atoms in a line, and I'll have 1 carbon atom as a branch, and then I can start adding OH. Now the OH could be added here. Okay, so if I just make more copies of this, so the OH could be added here, or it could be added to all sorts of different positions, right? So let's say the OH could be added on the second position. That's where the OH could be. Or we can have the OH bonded to the third one. That would still be different. Or we can have the OH. So we can also have the OH on the last two. So there would be, one second. So there will be 2 more. I mean, you could do the working on the same one. So the OH is what 2 carbon atoms are left. So the OH could be bonded here, or the OH is bonded at this end. These 2 ends are exactly the same. Like if the OH is bonded on this carbon atom or this carbon atom, they're exactly the same. It won't be a different isomer. So that is with this one. Can you identify or spot a tertiary alcohol? Tertiary alcohol is that the OH is bonded to a carbon atom that's on 3 sides bonded to carbon chains. So which one is this? In OH bonded to a carbon atom and all 3 sides, it's got a carbon chain.
So this is a tertiary,
Which one? Out of these,
the third one.
this one is a secondary because the carbon atom on one side, 2 sides is bonded to a carbon chain. This one is a secondary alcohol on 2 sides is bonded to a carbon chain. This one is a primary because the carbon is only on one side bonded to a carbon chain. This one is a primary as well. This one over here is a secondary because on 2 sides there's a carbon chain. This one is secondary as well. On 2 sides there's a carbon chain. This one is tertiary because on all 3 sides there is a carbon chain. Is that clear?
Yes.
Yes.
And the one
Yeah.
below it as well, right?
That's a primary because on this carbon atom only on one side is there a carbon chain. Is that clear?
Oh, okay. Yes, sir.
I said the more intelligent way of answering this question was because he was only looking for tertiary alcohols, right? So you should have started. I mean, this was a wrong approach because he was looking for tertiary alcohols. So we should have started with the minimum tertiary alcohol that is possible. Like we should have started with this. I mean, this was the least requirement. It had to be a tertiary alcohol, right? So he was asking how many tertiary alcohols can be formed. So you had 6 carbon atoms, right? So what you could have done was, I mean, this is the minimum requirement for a tertiary alcohol. So you've got 6 carbon atoms, so you could have added 2 more over here. That's one arrangement, right? The other one would be, since you have to make it tertiary at all costs, so there could be one carbon over here and 1 carbon on this side, right? So that's 6 carbon atoms, right? Is there any other combination that's possible? Apart from, I mean, these are the only 2 tertiary alcohols, or can there be more? They probably can't be because if I put the carbon anywhere else, it's probably the same thing, but just a flipped around version of the same thing. I can't take out because I just have 2 carbon atoms that I can play around with. Because the minimum requirement would, so I've just got these 2 carbon atoms that I can play around with. I can either attach the 2 carbon atoms to the same chain, or I can put them on 2 different chains. Because the minimum requirement for a tertiary alcohol is this thing. This thing has to be there. Is that clear?
Yeah.
Yes.
So I think the answer would be
Can I leave? Because I have a meditation to get.
ठीक है. Yeah, you can leave. So that's the minimum possible requirement for tertiary alcohols, okay? And so I think 2 would be the right answer. You can't have more than 2. So you don't actually have to. The better strategy for answering this question was don't draw all of them. That was a waste of time. You could have started with a tertiary alcohol and built on top of that. Like, how can you fit 6 carbon atoms in a tertiary alcohol? So there's only going to be 2. So the answer for that is 2. Okay. And so try and go through the papers I've sent you earlier. You can make sure with corrections and with the working. Please do hand in those on time, okay? By Friday tomorrow.
Okay, sir.
Yes, sir. Inshallah.
Sir,
Yes.
can we cover all the syllabus before May-June exam?
नहीं आप एक काम करो कि अटेम्प्ट कर लो, ठीक है? रिवर्स में थोड़ा क्योंकि अपना थोड़ा रिवर्स में पढ़ो because if you wait for the syllabus, then waiting for the past papers would be that would be too late, ठीक है? So what you should do is just say you're tertiary alcohols, ठीक है? You got an idea about tertiary alcohols, right? Even though you haven't studied tertiary alcohols. So when we discuss the papers, so when we discuss those questions, I'll go through that, okay, it's what that is. So you'll cover that, but at least your past paper practice would also be going on. Do you get my point?
Yes, sir.
कि टर्शियरी अल्कोहल समझ आया ना, टर्शियरी अल्कोहल क्या है?
Yes, sir.
तो अभी हमने नहीं पढ़ा, तो वो आगे जाके पढ़ेंगे, लेकिन बट वी विल probably have some idea, you will have some experience के what type of question we're going to get, ठीक है? तो a lot of things you've already studied in class as well, ठीक है? So मतलब we will मतलब it's not that we'll go through in detail, ठीक है? वो खोलेंगे, पीछे पढ़ेंगे कि क्या है, फिर उसके बाद हम आंसर करेंगे, ठीक है? तो इसलिए थोड़ा सा रिवर्स में पढ़ो. But the solving past type of questions is now more important, has a higher priority compared to studying the syllabus now. लेकिन with understanding, like, तो वो syllabus साथ साथ करते रहो, लेकिन you've got to focus on your past papers now.
Okay.
चलो.
Okay, sir. Allah Hafiz.
Allah Hafiz.
Okay, sir. Thank you.